In this lesson, we are going to graph a system of linear inequalities. We've already talked about how to graph an inequality, whether or not the line should be dotted or solid, shade to the right or the left, or above or below the line, depending on the test point. Now we're going to have more than one inequality, and we want to be able to shade all of the points that would satisfy both inequalities. So we're going to start by graphing this first equation, this first inequality. I'm going to use a cover-up method on this one to get that if I cover up 3x, then y equals 9. And if I cover up y, then 3x equals 9, so x is 3. If I were just graphing this one, I would then connect with a dotted line. And I would use a test point of 0, 0. To find that 3 times 0 plus 0 is less than 9, and that 0 is less than 9, and that would be true. And so I would shade everything towards 0, 0. Unfortunately, I'm not just graphing that. I'm also graphing my next inequality, which I'm going to find by plotting the 0, or plugging in 0 for 2x to get 5y equals 10, so y is 2. Plugging in a 0 for y to get 2x equals 10, so x is 5. This one's going to be a solid line. And if I were only graphing this one, again, I could use a test point of 0, 0 to get 0 is greater than or equal to 10, which is clearly false. So the blue line should not be shaded towards 0, 0. It should be shaded away from 0, 0. Now what I'm looking for is I want to find where would both be shaded. So where would anything be shaded? I need it to where it would satisfy both of the inequalities. And I can see that would be this region right here, because it is both shaded with black and shaded with blue. Now that gets a little bit crazy when I'm putting all of those lines on the page. And so this is what my graphs looked like before. This is the area that would be shaded. So that is the part where both 3x plus y is less than 9 would be shaded, and 2x plus 5y is greater than 10 would be shaded. Let's try another. For the first one, I get y is greater than 2x plus 4. Again, I would start at positive 4. I would use a slope of 2 over 1. And I would connect the dots with a dotted line. So that's that first line. For my second one, I would go to negative 2 and use a slope of 2 to go up 2 over 1, up 2 over 1. Again, I would connect the dots with a dotted line. And so that's my other graph. Now let's look at a test point of 0, 0. For my first inequality, I would get 0 is greater than or equal to 0 plus 4, essentially. So 0 is greater than 4. Which is false. So this first equation should be shaded over here. The second one, if I plug in 0, 0, I get 0 is less than negative 2, and 0 is less than negative 2, also false. So my second inequality would be shaded over here. Where on this graph are both shaded? Nowhere. So this is a no solution. You don't get those often, but this would be a no solution because there were no places on the graph where both would be shaded. For this last example, I want to talk to you about when you have more than two inequalities. So again, I'm going to go ahead and graph these as I normally would. I'm going to start the first one using the cover-up trick. So I would get that y equals 9, and I would cover up y to get that x equals 3, and I would connect those with a nice straight line. Now, if I used a test point of 0, 0, I would get that 0 plus 0, which is 0, is less than or equal to 9. 0 is less than or equal to 9 is true. So on this one, I'm just going to draw an arrow in this direction because I know that this is the side that would be shaded. For my next graph, my next inequality, I would again use the cover-up trick to get 5y equals 15, so y is 3. Cover up the 5y to get 3x equals 15, so x is 5. I would connect those dots and again use a test point of 0, 0 to get 0 is less than or equal to 15, also true, which means this would be shaded towards 0, 0 as well. Now I've got two more, but so far if I had to shade the region that was contained by both of these, it would be below this line and also below this line, so it would be the region shaded in blue. But now I've got these other two, and the other two are x is greater than or equal to 0, which of course looks like this line, and greater than or equal to 0 means it's positive. So all of my x values are positive, which means I can no longer use any of this. And y is greater than or equal to 0 is the line that looks like this, which means all my y's have to be positive, which means it can't be this area either. And so the area that should be shaded is contained in this little box here. It's below this line. It's also below this line, but it is to the right, meaning positive, and above, meaning positive. So this is the area that should be shaded. For our last one, all of the rest of the equations have been and, meaning they had to satisfy both. In this equation, it's a little bit different because we're dealing with an or. And so with an or, again, I would go ahead and graph. In this case, I have, if I divide by 3, that x is less than or equal to 2, which that's not the correct line. That's this line. So x is less than or equal to 2 is here. This line, I would say, is y, if I added x, is less than or equal to x, which is this line, starting at 0, using a slope of up 1 over 1. And again, if I used a test point on the first one, I would get that 0 is less than or equal to 2. And so that would mean that I could shade all of this. And on the second one, if I used not 0, 0, let's say I used 0, 4, I would get 4 is less than or equal to 0, which of course is false. So I should not shade this one towards 0, 0, so I would shade below. And because it's an or, it's actually all of this and all of this. So the only part not shaded is this region up here at the top. So that's the difference with the or, is it could be this one or this one.